Yeah, so that was also really not essentially migrated.
All right, so here we go. So before we get started, a couple of things off the top. So I will, after class this afternoon, kind of post up under this exam. Oh, there it is. Econ 371 exam. I'll kind of release those scores on the multiple choice take home portion. You should be able to then view all what the correct answers were. There was one question, I think it was question 7. I had to regrade it because there was technically 2 correct answers. So that should be regraded once those scores are posted to you. So there's technically 2 correct answers. I meant for it to be a select all that apply question. I know it said it's multiple choice, so it's only letting you select one of them. So as long as you got one of those right, you get that question correct. So you'll kind of see that. It might look a little bit weird on the scoring if you view your submission, but really either of those 2 correct answers, if you went with one, either one, it'll be counted as correct. Okay. Other than that, so Thursday, I'll bring the actual in-class portion exams with me. If you want to get it before then, my office hours tomorrow, you can kind of stop by and review that. But if you want that kind of take-home portion to kind of learn from like your earlier mistakes, I'll kind of have those Thursday if you want to get them as well. Overall, I know the exams are a little bit tougher, which is why I know some of the points in the other categories are a little bit easier. You have all these tools available to you. So I understand going into the exam, problem set grades, as long as you're putting effort in, your quiz grades are probably going to be a little bit higher. So when I was looking at the overall average, adding these up, I think the average was like a 73 after factoring in kind of that 3-point so that kind of gave me for filling out that pre-exam assessment. So I added kind of a 2-point curve, kind of putting that mean right at a 75. So it's usually where I like to kind of see that exam score average be. I will get these published, but I will also kind of post what your in-class portion was and also what kind of your total exam score was under this heading right here. I will then kind of adjust the grade book so that it's weighting that total exam midterm grade kind of according to the syllabus. Now, what I'm going to do is I'm going to update the grade book so that it takes on the weight of your midterm and your final, because ultimately that's what it's going to end up being. So it kind of gives you a hypothetical situation, which is if I do just as well in the finals I did in the midterm, this is what my grade would be. Now, obviously, you could do better, you could do worse. Kind of that's how I'll have the grade book set up. I don't know what other professors necessarily do. I think it's a little bit, I don't know if unethical is the right word, but if I don't kind of weight it, if I just weight it kind of what the midterm is not included to kind of carry the way of the final, usually exam scores are lower. So it's kind of give you an inflated idea of where your grade currently is. And I don't think that's really necessarily appropriate. You should kind of know if I do just as well in the next exam as I did in the first, this is kind of what my score would be. Okay. So those are kind of the changes you should expect to see on Canvas this afternoon once I get back to my office. I have kind of things already to post, but I just want to double check everything. Sometimes when I'm going back and forth, kind of making sure things get uploaded correctly. But you will see that all those changes on Canvas probably by about 2:30, 2:45. Okay. Other than that, like I said, I think if I do from memory, the maximum was like right under 100. So somebody very well. Once again, the mean was right around 73, kind of curving it by that 2 points, puts it right at a 75. Okay. If you have any questions, once I give those in-class portion back on Thursday, or if you're looking at kind of the take-home portion, you can always stop by office hours. Obviously, there's really only going to be kind of office hours after spring break once I hand those back. But if you want to kind of review that when we get back from spring break, you can. Now, this is where I give my little speech. So you can use all these tools available to you, right? On the problem sets and the quizzes, right? I know that almost all of you are using generative AI. I'm not an idiot, and also it'd be kind of dumb if you weren't, right? But if you're not understanding why it's producing the answers that it is, you're not going to do well in these exams, right? There's, I try to mention things in class. This is also where in-class attendance is important. What did I say one easy mistake was to lose easy points on the exam that I said that Tuesday before the exam? All else equal. I can't tell you how many people did not include that in their interpretations, right? You're losing easy points. I told you that, right? So this is where kind of paying attention to what I'm saying, right? Especially when we're doing these review sessions, that can be really important, okay? So I'm probably talking to the wrong group, but there's about half of us here today, right? So if anyone's watching the recorded lecture who's not here, well, you probably didn't get the grade you wanted, is my guess, because if I looked at that, I'll run a regression and probably use it as an example. In-class attendance is positively correlated with exam performance, right? I'll run the regression and bring the results next class, right? So, this is, once again, I'm probably talking to the wrong group here, but this is kind of my preamble before we jump into new material here, okay? Any questions for me before we kind of start in the next topic?
How many marks did you fail if we didn't try for holding for the
I think it was only like on the questions that it was only a half point. So, I mean, we weren't losing a lot, but it's like there was other things that I mentioned as well that people were making some of these mistakes where it was just paying real close attention. I mean, I can go back to the video, and then once you have the exam back, you can make the connection between things we covered that class before the exam and the actual questions, right? And so there's things I'm mentioning along the way. That's why I have that review class, because like I want to make sure you're doing as well as you can, right? I also, once again, can make those connections between that practice exam and the questions that were asked. Now, obviously, the numbers are different, the variables are different, but it's very, hopefully, this isn't like, hopefully most of you agree. I think that exam practice was fairly reflective of the types of questions you saw in exam. Now, obviously, it's a timed environment. It's, I understand that's going to be more difficult, but those practice materials, I can't state enough how important those are to kind of review going into that fine. We'll have a little more time to kind of review things before the final than we did for the midterm. Okay. Any other questions before we get going here? Okay. So we'll kind of be using these slides. I've got a bunch of different data sets because what we start covering this week, it's going to be an extension of what we've already talked about. You'll see today we revisit some of the material that we've really already talked about, just in a different context. But this nonlinear regression stuff, oops, I scrolled down too far. We'll really start using this week, but also once we get back from spring break. So it's kind of like week 9 and 10 is really nonlinear regression, but there's several topics within that category. So instead of like 1 week, it's going to take us 2 weeks to cover. Okay. So we'll have multiple data sets that I kind of jump in and out of throughout the next 2 weeks. You've got, where is it at? Oh, did I not add it? Well, that would be important. So let me do that right now. Be helpful if you had this is under the files tab. Oh, did I not upload it? Well, let's make sure you have this. Otherwise, you won't be able to work along. So go here. I just uploaded the slides. So let's go. OneDrive, go to 371, 9 and 10. Make sure that you guys have this do file. That would be helpful. Sorry, I thought I had everything up there, but with so many data sets, I missed the actual do file. So we'll add in, so it's easy to find, that do file. So that's the do file we'll kind of start working with today as well. Okay, so that nonlinear spring do file and then our nonlinear relationship slides. So starting out in the slides, right? Up to this point, we've only talked about estimating what we would call linear relationships. Anytime I was drawing out this line of best fit, it had this kind of constant slope, right? It was linear, okay? Now, that's not going to be every situation, right? So we'll start out with a simple linear regression. We'll then kind of go to a multiple linear regression. But let's think about an actual example where I'm trying to predict the length of a fish, right? So I think I have bluegill here. Found some weird data set with bluegill lengths and ages, right? So the age of a fish, as something gets older, anything in biology, as it gets older, its size grows, right? So as I'm thinking about trying to predict the length of this fish, as age goes up by 1 unit, theta 1 is the predicted increase in its length. Now, you could think of this in the context of people as well. My son right now, who's like almost 1.5, his height every month is increasing, right? Now, what happens once you turn 24? What happens if you get an additional year older? Your height stays the same. So we know that it's not linear, right? We know that initially, any biological organism typically grows very quickly, right? And then that kind of tapers off. So if I, think about like keeping it linear, I would think that it's likely going to have a positive relationship, which if I run this regression, sure enough, it does. For every year, I think here this probably wasn't year of the fish, it was probably something like the month of a fish, goes up by 1 unit. So every month it's older, its length, and I don't remember if this was measured in millimeters or probably millimeters, increases by 44, right? Highly statistically significant. Just because we find a highly statistically significant effect from a linear regression, that doesn't necessarily mean that the relationship is linear, okay? So if I'm looking at kind of this data, so this is a scatter plot of this fish data, I could estimate a linear line, but you'll kind of notice like what might be better is if I could get a non-linear relationship. So maybe to kind of draw something out that'll relate to class here. And I'll show you an example and state here in a second. But if I'm thinking about not just this class, but any class, the hours I study and my exam score, right? If I don't study at all, right, it's probably not going to be very good. As I initially put in like that first hour, well, I know I have some idea of what's going to be asked. I'm studying probably the things that I didn't know the most. So I'm going to see like a huge increase from that first hour study. Now, as I study more and more, eventually I get to this point where like I've reviewed everything. Now if I put another hour in, it's really not going to impact my exam performance much by the time I've studied 40 hours. Or hopefully you weren't studying for 40 hours, but you get my idea, or you get the idea, right? So if I had this data, and let's say the scatter plot looks something like this. If I could draw a line that wasn't linear, I can get this line or my predicted Y value that is going to give me a better fit of what this actual relationship is. In fact, if I tried to estimate this as a linear relationship, we can kind of think about if I had to draw a line that kind of best fit this data, it might be something like this. Okay. Now, what's the problem going to be? Well, on average, right, maybe my errors still have a value of 0, but notice for really low values of X, all my errors, the difference between the predicted and the actual Y values are going to be negative. I'm too high. For really high values, all of my predictions are going to be too high. Now, in the middle, my predictions might be too low. So on average, I'm still getting an expected error term, which when we run these regressions, the expected value of the error should always be 0. Right? That won't necessarily be the case if I'm forcing myself to run a linear regression when in fact the relationship between these two variables is nonlinear. Okay? I'll still have an expected value, an error of 0, but for different values of X, I know I'm going to be making probably negative errors here. And then for some of them, I'll only be making positive errors.
It's like homoscedasticity here, or is that like just
so homoscedasticity didn't refer to the expected value, right? Expected to be kind of the variance. It could, but even here, I try to draw the variation in errors, still homoscedastic, right? It's just that my actual predictions are what's going to be off now. It's not just the variation in my predictions, errors, it's the actual errors I'm making. So we don't want to be constrained by these simple linear regressions. We want to allow ourselves to be able to estimate nonlinear relationships. Okay. So let's go ahead and think about these bluegill again. Okay. So I know that, my errors are going to be different depending on what point I'm looking at. So what do I want to do? Well, if I have an equation that's nonlinear, what's one easy way to capture that relationship? I can include a. So if a line has curvature to it, it's not just y is equal to mx plus b. I would also have a squared term, right? It allows for that slope to change as x is going up, right? So what do? I essentially include an additional variable. It's almost like when I was running this simple linear regression, I was leaving out an important variable that mattered, or I had a what? If I left out a variable that mattered, what kind of bias would I have? Omitted variable bias. So if I leave out this squared term, I treat the relationship as though it was linear, right? When in fact it was nonlinear, my estimate of this relationship for the linear term is going to be biased, right? So I've got this kind of omitted variable bias, which looks a little bit different, but it's basically, I should have been including a squared term to actually capture this causal relationship of age with the length of the fish, or age with human height, or hours studied with exam performance. So what do you think maybe something I'll initially do? If I have age, how can I create the age squared variable? Just take age and multiply it by itself. So if I've got the data for the linear relationship, automatically I have the data for this important omitted variable. Why not include it? Okay. So I can include this squared term. What's going to tell me whether or not the relationship actually is nonlinear? What would be true about a coefficient here? So if I think it's nonlinear, I think the squared term matters. What would tell me if the squared term matters? It's coefficient. How do I know if that coefficient is anything other than 0? If I can reject the null. So I'm basically running this regression, looking at the p-value of the coefficient on the squared term to determine, does it have a statistically significant effect? Now, one thing I'm all automatically going to get, if I include an additional variable, if I treat this as nonlinear, what's always going to happen to some statistic in my regression? R squared will always go up. So now we can start to think about what I want to do. Look to see if I've included a variable, what gets penalized for having more variables. Did the adjusted R squared go up? So these are all, once again, we're going to be reusing a lot of the things we've talked about, just kind of a slightly different context. Okay. So if I run this, nonlinear relationship, potentially I get that the squared term has a positive coefficient, or I kind of have this slope where it's I guess decreasing at an increased rate, or I have kind of this negative coefficient, right, on that squared term, which would tell me that kind of this is increasing at a decrease, right, or convex concave. Basically, depending on the variables, right, it might not always be like that one relationship I drew. It could be kind of going the opposite way as well. Right? In fact, still a little bit, sometimes my classes line up perfectly. So in my introductory micro course today, what does this look similar to if you go all the way back to very basics of cost structures for firms? As I hire more workers, gains from specialization, diminishing returns, this looks like a marginal product curve. So if I had the number of workers in my data and I had output, I could estimate a marginal product of labor curve by including a squared term on the number of workers I had. Or I can think about, what does this look similar to? Initially, if I've got gains from specialization, my costs are going down, and then eventually diminishing returns take over. If I had output and cost data, I could estimate a firm's marginal cost curve by including a squared term. All right. So this is why it's applied econometrics, right? Because you can apply it to these other economic things that hopefully you're talking about in other classes. It's just you actually have to have the data. So back to kind of our bluegill. So if I was thinking about this, I know that as a fish gets older, it's going to grow in length, right? So you get older, your height's going to go up, but it's doing so at a decreasing rate. Right? So what would I expect the sign of beta 2 to be? So I know that beta 1 will likely be positive. As someone gets older or a fish gets older, it's going to grow in size. But that rate, it's growing at a slower rate. So I'll probably jump the gun in terms of the slides here, but I think it makes sense in the context here. And maybe we can do this for both examples. So if I have the length of this fish, and I now start treating this as though it's a nonlinear relationship, what is the change in my y variable in respect to my x variable? Or what is the change in length in respect to age? This is starts with a D, derivative. That's all we're doing. We're looking at a marginal effect. Before, we just had a linear term, so we're just looking at that single coefficient. But if we have a nonlinear relationship, it's basically just a derivative of our y variable in respect to this x variable that we're allowing to be nonlinear. So that would be what? Our estimate for beta 1 plus 2 times our estimate for beta 2 times age. So if this is the marginal effect of being 1 year older, we said we would expect that that marginal effect is decreasing as the person gets older. So beta 2 here we would expect would be what? This is the total effect of being 1 year older. As I get older, that effect is going to be going down, where that kind of squared term would have a negative coefficient. Now, I'm not going to ask you like a question where I expect you to kind of know these relationships. We're going to start to eventually look at the actual data to see, is that coefficient, when I run this regression, I can see, is it actually positive or negative? Okay. Any questions on this idea before we keep moving? Okay. So let's look at some actual output here. Okay. So if I run this nonlinear regression, well, first of all, I'm going to go all the way back where we just ran it as linear. We treated it incorrectly, right? So I had a statistically significant effect, and then the way we interpret this is for every 1 unit increase in age, the predicted change in Y was 44.7. This is the coefficient on the linear term, or beta 1. Now, this is going to be containing some omitted variable bias. So when we run instead our nonlinear regression, where we've included age squared, what happens? All right. Well, we can scroll all the way back, but what hopefully happens is we see our R squared goes up by a lot. Right? In fact, I don't think I put it here. We'll kind of jump back and forth just to make this easier. So originally my R squared was 0.7, right? Now if I come down here, it's 0.75. So I'm better explaining that relationship between length of a fish and age by including the squared term. So that's one thing we can look at, the R squared or the adjusted R squared. What's the second thing I could look at? Well, does the coefficient on that squared term have a statistically significant effect? Does it here? Yeah, p-value 0. We can reject at any level. Now, here's where we get kind of hard to interpret these coefficients, because the actual interpretation I need to make would be a combination of those two. The actual effect of age, if I'm 1 year older, it would change my predicted length by this amount, but it would also change it by changing the age squared variable, which is why when I wrote out that marginal effect, now the total effect of age going up by 1 unit isn't a single coefficient. We're going to have to use both of those, right? And in fact, to get the effect of being 1 year older, or month, whatever this was for fish, this is going to be my actual effect on Y. We're going to have to use both of the coefficient on the linear and the nonlinear term now. So interpretations get a little bit tricky, right? So I would never ask you to make the interpretation of the linear or the squared term, right? I would ask you, what's the total marginal effect of being 1 year old? This is how we would find it, right? That marginal effect now depends on the actual age of the individual. If I'm 1 year older, think about a human, if I go from the age of 1 to 2, the change in my height is going to be much larger than if I'm going from the age of 24 to 25, right? So the actual marginal effect will depend on my age now. Okay. Now we could still use not just the p-value, we can still do our critical value approach, compare the absolute value of the test statistic, the absolute value of the critical value. It's another common mistake I saw in the exam. If I just gave you the confidence interval here, why can you tell me that the age squared variable had a statistically significant effect? What is not my interval? 0, right? Let me think if there's anything else I want to say here. I think we should be pretty good at this point. Any questions on this before we keep moving? Okay. So I already did the kind of exam performance example. I jumped the gun a little bit here, and we'll jump to Stata here in a second. But let's think about if instead I had a different regression where I wanted to predict the score on some standardized tests. So this is maths. I don't know. I forget. This wasn't the SAT. It was some like states, like iRead or whatever. It's iStep. I think it was actually from North Carolina, and they had some measure of student effort. Right? So as it's kind of the same idea of hours studied and exam performance. As I put in more effort or more hours studied, that had a huge effect on my score on this test initially. But as I study more and more, the marginal effect is going to be decreasing. So we might think about it's likely that there's a squared term that needs to be included. Okay. Now, I said if we only include the linear term, we're going to have some omitted variable bias. So we'll kind of take a look at this here in a second. But for now, we'll just think about, I want to include this squared term. Okay. So I can compare the R squared for my regressions, right? I can also think about, well, if I'm adding additional terms, if I'm comparing models, I could also run some joint significance tests. So maybe I don't just include a squared term, maybe I also include so what's the next step? I can include a cube term. If I've included a squared and cube term, I can do a joint hypothesis test for whether or not they simultaneously had an effect. So think about it this way. Let's say I run this regression and the coefficient on the squared term, I can't reject, right? Well, that doesn't mean that I necessarily have a linear relationship. It just means that the quadratic relationship doesn't fit it better. If instead I think maybe it's not quadratic, it's cubed, well, then I'm including I can't include the cube term without including the squared term to make it kind of a cubed relationship. So there, in order to say whether or not it's a better relationship to estimate it as a cubed, include the cube term compared to just the linear relationship, I now need to run a joint hypothesis test, something we've already talked about. Would the coefficient on the squared and cube term be jointly significant? Okay. So we'll start to kind of take a look at this and stating here in a second. But once again, we can have some different scenarios where can I say that I should be estimating this as a nonlinear relationship at the 99% level here? So at the 99% level, can I say that that squared term actually was statistically significant? No, the p-value is greater than alpha. So what that would suggest is I actually shouldn't be using a nonlinear relationship here. I should be using just the linear relationship or go out and search for other nonlinear relationships. Here, I've only ever talked about the cubed one. On Thursday, we'll talk about logarithmic relationships. Okay? So it doesn't have to be that we're always going to reject, right, the null for that squared term. Sometimes we might not. And that would suggest that we shouldn't be including it. Okay? So here I'm going to compare these kind of side by side. I know it's a little bit smaller, but knowing that that squared term was not rejected at the 99% level, what could be happening to my R squared? So it's still going up, but if I compare the adjusted R squared, if it's not really significant, then including the squared term, my adjusted R squared could actually go down. I know that I can explain more variation by just including more variables, but my adjusted R squared penalizes me for using them. So here's a situation where, okay, the adjusted R squared still increases, which kind of makes sense because even though this isn't statistically significant at the 99% level, it still is at the 90 and 95. A different thought experiment might be, and I think I'll have some examples once we jump to Stata, what if this had like a p-value of 0.4? Highly statistically insignificant. There, we could actually see, even though I included an additional variable and R squared went up, I could see my adjusted R squared go down, right? Which would be a suggestion that I should not be using that squared model. Okay? Now here it doesn't quite work out because it is not statistically significant at the highest levels, but it still is statistically significant at 90 and 95. Okay. Excuse me. So the adjusted R squared is greater, but that doesn't necessarily always have to be the case. Okay. So I think here I'm going to, I already mentioned this, but we can include, well, before we go to Stata, we'll go through this. So we can kind of compare that linear to the nonlinear model. Maybe I'm like, okay, I don't think the quadratic model, it's not statistically significant at the 99% level. Maybe I want to see if there's a cubed relationship here, right? So maybe initially when I'm studying for an exam, maybe like I'm getting through the easy stuff first. And that doesn't really help me get the hard questions right. So maybe initially when I'm studying, the returns are not very high. But then as I study more and more, I start to get in more complicated material. Maybe then it starts to like increase. So maybe I have this kind of cubed relationship, right? Well, now what I do, if I want to compare the cubed model, right, to just the linear model, what I would need to do is a joint significance test for the two added variables, which are now effort squared and effort cubed, right? Or is beta 2 and beta 3 jointly significant, or are they both not equal to 0, right? We always start out assuming they're both equal to 0. We run this joint significance test to say, can we reject that? So all I have to do here, if I'm running this in Stata, I still use that test command. So I run my regression with all the variables. I want to test the squared and cubed term. Are they jointly significant? Here I end up with a p-value of 0.27, which would suggest what? Should or shouldn't I be using that cubed model compared to the linear model? Shouldn't. I can't reject it at any of my conventional levels. Okay. Now, if it did have a p-value that was less than 0.1, 0.05, that would suggest I should be using the cube model to estimate this relationship. Any other questions before we keep moving here?
That R squared is lower than the previous R squared.
Yeah, so why, first of all, go back here, right? Why might that R squared actually go down here? Well, first of all, I had slightly different data set here, a slight number of observations. But also, if I'm thinking about the amount of variation I can explain, if I go back here, this was kind of my effort squared, right? Actually, why does that? Does it go down? 0.02. I must have been using a different data set here, because you're right. If I include a cube term, it should only ever go up, right? Well, that's not technically true. I wouldn't expect you to know this, but this is, I'll give you somewhat of a loose explanation as to why, since you asked the question. Have I actually used more data in this regression? Still using the same variable. So if I incorrectly, once again, I won't go this far into what I asked you. I simply talk about, like, did the R squared go up or down? Why could the R squared go down here? If I'm estimating the wrong relationship, which is what that joint significant test told me, I've created additional variation that now causes my predictions to be even worse than before. So now my predictions will be able to explain even less of the original Y variable. But it's because I haven't really included an additional variable. I've just scaled the same variable. Do you understand what I'm kind of saying? So, like, I'm basically creating some inherent variation in the data where I'm still using that same variable, the same collected data. I'm just transforming it by including the squared and the cubed term, which might now just create more variation. So, and give you kind of a visual that'll help. This is a good question, right? I wouldn't try to trick you if I'm just giving you state output and asking you. We would typically think about, as we add more variables, we would see an R squared go up. But let's say I did, in fact, have something that looked like a linear relationship, right? When I include this cubed term, it's basically like I'm trying to estimate this relationship and I'm forcing it to look something like this. So I've created even larger errors, which now my RSS, or that sum of the residuals, is now even higher, which means I can't explain as much as I was before because I've now just included this additional variation in my causal estimation. So yeah, so you can get some weird things if you use, this only works, or this only happens if I use a model that I shouldn't be, right? Anytime I use a model that has some statistical significance, notice what happened to my R squared there. It went up, right? And sure enough, that squared was statistically significant at some levels. But as soon as we use the model where it wasn't statistically significant, then I could technically see my R squared go down. That won't always be the case, but I could see that happen. Any other questions at this point? Okay, so let's see here. Let's go to Stata here. I'll kind of show you some of the commands. We'll look at things a little bit different. So I have kind of this fast data. So just kind of as a starting out, and this is where it's not going to be what I want because I'm on a different, I'm not on my personal device, and I copy and paste that path. So we'll go open that fast data, kind of make sure I've got my new global that's not my personal device, but on OneDrive. Open that up. And I'm now going to think about, it's a very simple data set. I've got, I don't know, age, length, weight of the fish, etc. So I'm going to be thinking about, if I just run this as a linear regression, nothing looks different, right? Y variable, X variable, right? If I want to include a squared term, there's a couple different ways of doing this. So the first way is, how do I create a squared variable? I generate a new variable, which is age times age, right? That's fairly easy. Or, I could technically take, I'm just going to call this age squared 2. I could just square it, right? Both of these commands should generate variables that simply took the age and squared it. So both of those would work, all right? So if it's easier for you to think about a squared as a variable times itself, or I could just square a variable, right? Those are doing the same thing. I would then run a regression using the linear term and the squared term. So I don't ever just want to include the squared term, right? I need to actually, if I want a quadratic relationship, I have to have both the linear and the squared term. Okay, this is, going back to like a math course you took probably early in your college career. So if instead of this kind of fish example, so this is just kind of setting up basics of how we create these squared terms, I could even think here, what if I wanted to include a cube term? I'd create a new variable that was what? Age to the third power, or age times age times age. And then I would include that variable. So let's say here, I create this variable. We already looked at this regression output in the slides. But let's say now I include the linear, the squared, and the cube term. So I run these two regressions. So I look here. Here's my quadratic model, just including the squared term. My R squared was 0.75, and the squared term was statistically significant. If instead I'm like, well, should I be using this, or is it maybe cubed? I don't know why I would believe that about fish and age, but let's just say I want to check it, right? Well, notice my R squared just barely goes up, but my adjusted R squared is going to go down a little bit. Because this is, though, even adding in that cube term, maybe had a little bit, right, could explain a little bit more of the variation. Our adjusted R squared gets penalized for the fact that I included essentially an additional variable, right? So even though I add a variable in to kind of look at this different type of nonlinear relationship, I don't really want to be comparing my R squared. I actually want to be comparing my adjusted R squared. So if I do that, which of these models is actually better? Whichever has the higher adjusted R squared, or the model that just had a square term, not the cube model. Now, what might also suggest that is if I look at the statistical significance of the cube term, what happens? Nowhere close to statistically significant, right? So this suggests that not only did my adjusted R squared go down, the coefficient itself on the cube term doesn't have any statistical significance. This isn't the model I should be using to capture that relationship between age and length. Once again, I don't even know what the intuition behind how an organism would grow that way would be, and which is why it comes up as not statistically significant. Okay. Any questions on anything here before we keep moving? So I'm going to be adding some stuff into this do file. The one I gave you is just kind of a base where we're going to kind of work off of it and start adding some things in.
I don't know if this makes sense. Finding this, but would you ever, like, if you're looking at it through like age cubed, would you ever omit the plus squared variable? Will that, or like, will that?
No, so if you're building higher order functional forms, right? I'm always going to include, if I include the square term, I should be including the linear term, right? And if I'm including the square or cube term, I need to be include the linear and the square term, so on and so forth. Okay. Any other questions? Or keep moving. Okay. So the next data set we'll look at is kind of that test score data. So we kind of already looked at something here where I could look at kind of this cube term. So all I'm going to do here is open this data set up, run the simple linear regression, create the squared term, create the cube term. Now, once again, I already showed you. You can do this by taking things to powers. If it's easier to think about, though, you can always just multiply the variable by itself. Okay. So I'm going to run this regression, all these regressions. And the last I'm going to regress is this one with the cube term. Okay. So if I want to test for the joint significance, it goes back to exactly what we were doing before. If I want to test the statistical significance simultaneously of two variables, I use that test command. Right? It then produces me a p-value that I can use to test for that joint significance. Right? So here, that was kind of what we saw in the slides. Okay. Now, I'm going to add something in here, right, where I just want to kind of go to show you, and then I'll kind of come back here and do something different. I can look at this, right? So maybe I look at this relationship, and effort and effort squared, I'm using the quadratic model. What could exist, and this is where it gets very difficult to think about, so it's more so just knowing that this can happen and not understanding what the omitted variable bias would be. But as I include additional controls, so let's say I think that these other things matter in predicting someone's math score. Grade size, their gender, whether or not they went to a charter or magnet school, which I believe in these states were like basically like if you got hired, I forget which one's which. Magnet schools, I think you had to have high performance to get into, and charter schools, you had to pay money, right? So you're kind of correlating that with like wealth of the family. So I think these things matter. What could happen is if I omit these variables, they could cause a different bias in my linear term than they do for my squared term, right? Now, it gets hard to think about why that would be the case. All we need to know is when I include these additional control variables, it could change not just the coefficient on the linear term, but also the squared term, okay? So let's think about here what I want. I'm gonna, oh, what did I have here? Okay, this works. So I'm going to regress. I want to change the order of this a little bit, just so we can have this kind of comparison. I'm going to cut this, paste it. We're then going to look at if I simply estimate this as a linear relationship, and then I include additional controls, right? So, and we could even kind of treat these the same, right? So we've got, here's my kind of like pre-exam stuff. I'm looking at this simple linear regression. I then include all these additional controls. Well, now my interpretation is it's putting in one more unit of effort, increases my predicted mass score by 0.5, but now holding all else constant. Now it's still about 0.5, but when I include these additional controls, it must be that they had some correlation with this because it changed my estimate a little bit. Now, not much, right? So here I could see like it didn't really change a whole lot when I included these additional controls when I was estimating the relationship as linear. Now, if instead I run this simple regression where I'm just looking at is the effective effort quadratic? And then I'm saying, how does that change if I add in these same additional controls, right? So now we're going to look here. So without the additional controls, it looked like the effective effort, although not quite statistically significant, pretty close here, right? P-value is 0.11. We're not quite at that threshold of 90% level, but pretty close. Now, if I look at these estimates on the linear and squared term, they're a little bit different than down here, right? So they're both, in fact, a little bit lower or closer to zero, right? Now, so this one, right, had some positive bias built in. The other one must have had some negative bias. So this is where the additional control variables can change the linear or nonlinear coefficients in the same direction, different directions, right? We don't know, right? So what's now happened is both of these, when we include these additional control variables, not only did the size change, and right in different directions, this became a smaller positive value. This became a smaller negative value. Right? I mean, both getting closer to zero, but technically a smaller negative value is an increase, right? So we did have different directional changes. But also, what happened to the statistical significance of both estimates? The p-values both went up. So even when I'm estimating this, I might find that when I include additional control variables, I thought that this was a statistically significant relationship before, or at least it was pretty close to it in terms of that square term. Now it's even further away from 0.1. Right? So I'm just kind of using this to show like control variables still matter, right? They're going to influence both the size and the statistical significance of both the linear and the square term. And they might not always affect both equally, right? In this case, the coefficients change in different directions. Now here, both the p-values went up. You could have that where maybe one goes up and one goes down. That could happen as well, okay? So I'll try to look at more examples and maybe we'll see one of those kind of pop up in those. All right. Okay. Any other questions on this before we keep moving here? Now we might also see, it kind of gets hard to look at this or think about this, but if I added more control variables just to kind of relate to things we talked about before the other exam, what should happen to my R squared? If I add additional controls, it should always go up. Right? So that's another thing we can kind of see here from the data, just kind of relating to things that we've already talked about. Okay. Now let's go down here because I think this is an interesting one. So let's use this COVID county data. Right, and we're switching up our examples of that. Now I'm going to scale my population variable. So here, before, oops, let me run this regression before I scale it, just so we can revisit some of the things that we talked about before the exam. So I'm just going to run this regression. This was the number of COVID cases in 2021, and this was the population of the city or the county, I believe it was. Sorry, not city, county. I mean, if you're looking at larger and larger populated counties, what do you think would happen to the spread of a disease? It's going to increase. But if I go from having 100 people or 1,000 people to 2,000 in my town, that might have a much larger effect than if I go from having 1 million to 1 million, 1,000, right? That's not a very large kind of percentage change. And so maybe the squared term matters here, right? So if I run this regression, and I find this coefficient, this is the effect, I think, of having one more person on the problem, and then the effect on the number of cases. Right? So like basically of every 10 people, we're getting about one more COVID case, right? Or every one person was increasing the number of COVID cases by 0.13. This was, when COVID was kind of pretty raging, right? It was at its height. So if I scale this population variable, what should happen? So if I divide it by 10,000 here. Now every unit change is going to represent a change of not one person, but of 10,000 people. So what should happen to the sign of my coefficient? Well, if it's no longer having one person, it's having an additional 10,000, the effect should go, oops, didn't run the regression. I just created the variable. So here, I can copy and paste. Oh, come on. Now when I run this, well, where were we at before? There we go. All right. So now if I run this regression, oh, I deleted a bunch of stuff, didn't I? Oh. That's what I want. There we go. So now I'm going to copy and paste the same regression down here. After I've scaled the variable, what's happened to the sign of my coefficient? It's been scaled up. All right. Now what should happen to my R squared? If I scale a variable, my R squared should. Have I changed the underlying data at all? No, I've only scaled it. So even though the coefficient changes, because that's what we interpret, the actual variation we can explain in COVID cases should remain exactly the same. Okay. So scaling variables, also what shouldn't change? The statistical significance, right? I get the same exact t-value. Now, what will also change, if I scale the coefficient, the units for my coefficient have changed. What else do I use to create the test statistic? My standard error. So if the coefficient went up, to keep the test statistic the same, the standard error must have also went up. Sure enough, it does. So once again, just kind of revisiting some old stuff that we've talked about. Now, maybe what's a little bit more interesting, right? So I've got this scaled variable just so it's easier to think about. We generally don't have like one more person in an area. We have like 10,000, okay? Instead of creating these new variables, which is fine, but we'll start using this in other stuff we do for nonlinear relationships. And with large data sets and large numbers of variables, this can sometimes be more helpful. When I start to create variables, especially if the data set is really large, that takes up a lot of memory, right? So if I can avoid it, I don't want to actually put new variables in my data set, right? I want to create them temporarily and then kind of state and kind of dump them out. So in this regression, if I want to include a squared term, what I can do is say, take this continuous variable, right? So C dot tells Stata, this is a continuous variable. Population is continuous, right? The number of people is increasing. And then if I use this double hashtag, and I put C dot population here, what it does is it takes this continuous variable population, includes the linear term, multiplies it by itself, and includes the squared term, right? Now, we'll use this syntax later on when we start to look at like what we call interaction terms. For now, we're just talking about nonlinear relationships using like squared or quadratic or cubed models. So we can do this, and it doesn't have to create a new variable in my data set. It doesn't have to create population squared as a new column in that data set. So I can kind of prove this to you. Right? So let's say I kind of created this variable, probably not the best practice. Whoops. If I can spell. All right. And then I run this regression where I'm trying to predict the number of COVID cases in October 2021. I include population, what did I call this? Underscore SQ. Okay. So if I create the variable and run this regression, what didn't I do? Did I spell something wrong? Oh, I gotta put it reg, right? I'm generating a new variable here. So if I generate that new variable, run this regression, all right, here's the kind of output I get. If I use this syntax, it should essentially do the same thing without having to create that population squared variable. Sure enough, it does that, gives me all the same statistics. Now, the output looks a little bit goofy, right? So what it's telling me is here's the linear term of population, and then here's the square term where I took the continuous variable and multiplied it by itself. So the output looks a little bit different, which is why if you have small data sets, sometimes it's easier to do this because you can call the variables something that look nice and easy to present to someone who maybe not be the most well-versed in Stata output. But if you're talking to other like data scientists, researchers, they're going to know what this means, right? And they're giving you the same values. It's really no difference in the results. It's just one has a prettier name. And there's a way we could rename this, but it's kind of outside the scope of this class. But I figure I just kind of mentioned that. So we now kind of have this shortcut, right? Of creating those squared terms. We can just run that, or we can actually do that in the actual regression itself. Doesn't have to create a new variable, does it all behind the scenes. Okay. So this is where it'll get a little bit trickier. So is everybody on board up to this point? Okay. So if I go back to that linear regression, where I didn't include the squared term. When I included the squared term, what happened to my coefficient? It went down. So what must have been true about the bias that existed when I didn't include the squared term? Well, my naive regression included this bias. So if it was too high, the bias must have been positive. So let's think about what the bias would look like if I had an omitted variable, which was this important squared term. If I was incorrectly estimating this relationship as linear, even though it should have been nonlinear. So if I think about here, I had kind of those COVID cases. And if I ran the naive regression, where I treated this as linear, what would my omitted variable bias be? Well, the estimate I would see would be equal to the true effect plus the effect of the variable I left out or omitted times the covariance between the variable I included and the variable I omitted over the variance of the variable I included. So writing this out in the context of our example, if I had this important omitted variable, I'm going to kind of abbreviate here, which was population squared. Okay. How could I put a sign to this bias? Well, what's the bias going to be? It's the effect of essentially beta 2, which is what would the effect of population squared have been, okay, times the covariance between population and population squared divided by the variance of, well, what was the variable we originally included? Just population. Well, here's kind of where this gets, nice to think about. So if I'm thinking about the covariance, as population is getting higher, right? So if it's increasing, what would the covariance be between population and population squared? Well, population can only ever be positive. So when I square it, it's always going to be positive. So what's true about the covariance between population and its squared term? It's always going to be positive, right? If I square a positive value, it's always going to be positive. That covariance should be positive. Variances are always positive. So if I ended up with an estimate that was too high, we said we had a positive bias. What must be true about the effect of that squared term? The coefficient must be positive, right? Or that this is increasing at an increasing rate. Okay. So if we look at these results, hopefully that kind of lines up. Sure enough, when we included that squared term, it was positive, right? So it would get a little bit harder to think about this if I had a continuous variable that could be negative and positive values. I would still want to use that covariance matrix, because if you think about it this way, if I had a negative value, if it's becoming a smaller negative value, when I square it, right, it's now going to be positive. But for the positive values, when I square it, it'll be positive. So that covariance might look a little bit different. But we could still do that by running a covariance matrix. So we said, how would we, even if I wasn't sure how to think about this correlation, we've already done this, right? Looking at other omitted variables. So I could run the covariance matrix. Sure enough, it tells me that the covariance is positive, gives me the variance of the variable I included. I could actually still calculate the sign of that bias, even without having that naive regressions results, right? What would I do? I'd have my covariance between the two variables. I'd have the variance of that variable I included. And I know the coefficient of that variable I omitted. I would basically just be taking those three values, plugging them into my equation, okay? Just like we were doing before. It's just now the omitted variable is the squared term, okay? So where am I getting these? It's the covariance between the included and omitted variable, which is now the squared term. The variance of what was the naive regression, I treated it as though it was linear, so just the linear term. And then it would be the coefficient that's on the omitted variable, which is now the squared term. So when we're thinking about the output, where will we get those values? Well, here's the coefficient of the variable if I did omit it, right? It would have been 0.132. Here's my covariance between the linear and squared term. Here's the variance of the squared term, or sorry, of the linear term, right? The one I originally included. So it's the same thing, just the omitted variable is now the squared term as opposed to just some other random variable. Okay. Is that clear? I know I'm kind of bouncing back and forth. Are there any questions there? Yeah. Oh, in fact, I could do this for you here, so I'm not bouncing back and forth. So this is where I could use that display command. So what should the bias be? Should be the effect of that omitted variable, which was the squared term. So about what, 0.132 if I'm rounding this, times the covariance, which was what, 521218, divided by the variance of the linear term, or the variable I didn't omit, which was 1112.25. Right? So if I run this, what should I find? Well, it should be the difference between that coefficient I ran when I did include the omitted variable of the squared term and the original, where is it at? Coefficient here. So what? 1333 minus 1271. So I'm right around 60-ish, right? So if I hit this, hopefully, I'm getting something right around 60th, right? I was rounding pretty egregiously in my head there, but right, that should give us a sign of that bias, just like if we were doing this with any other omitted variable. Okay. Any questions over what I was kind of doing here? Okay. Oh, what do I want to do here? This is kind of difficult. Well, let me see where I'm at in the slides, because I think there's some things I want to mention. So we can look at marginal effects. Kind of already alluded to these a little bit. I think we'll stay in Stata here just for the sake of what we're doing today. So let's go up here. So I had this kind of I'll just show you. If you ever want to block out multiple lines, instead of having to put a double backslash in front of every line, if you do backslash star and then star backslash, everything in between that, it'll treat as a comment. Right? So sometimes I'll do this if I don't want to actually, maybe we have time for this or maybe we don't. So I don't want you to think like you have to know this. So just a shortcut for me to treat this all as comments. Now, some of this I can actually run. Right? So I wouldn't expect you to do this in Stata. I might ask you to do this by hand. So we already talked about when I have a squared term, my marginal effect would now essentially be the derivative of my regression equation in respect to that variable that I had a squared term. So now my marginal effect will depend on that variable that I squared. Right? So what Stata can do is if I run a regression, so let's say, and the only way that I can do this is if I use this kind of syntax where I don't create the actual variable itself. I have to use this kind of C dot double hashtag C dot, right? So it includes the original population variable and the squared term. But if I run the regression to include the squared term this way, if I run this margins command, and I tried to kind of write out the just general syntax here, this dy dx, what does that sound similar to? A derivative. So it'll run this regression, look at the population variable. It will take a derivative of the regression equation in respect to that variable. Basically, it has the marginal effect behind the scenes, right? So we said before, let's say in this example, what would my marginal effect be for population? Well, if I take a derivative of my y variable in respect to this x variable, it should be my estimate on beta 1, 2 times the estimate for beta 2, times that population variable. So Stata does this behind the scenes. It has those estimates because it just ran the regression. It then plugs in different values for population and reports to you what the marginal effect would be at different x values or different values of that variable of population. So that's what it's doing behind the scenes when I use this margins command. And then it says, calculate those marginal effects from 1 to 1,000. Now, I'm going to show you this here. This is going to be a mess. So I'm going to show you how to change it. All right, so if I do this, it's going to take it a minute. In fact, I kind of forgot these computers suck compared to most of our personal. There we go. Take a while. What did it just do? It calculated the marginal effect at a population of 1, 2, 3, 4, 5, 6, 7, all the way to 1,000. That's pretty wild, and I probably don't really need all of those values. So what could I do? This is the starting and stopping value. Maybe I just want to see how is this marginal effect changing, but like I don't need to see all those values. This will be kind of the increment that it changes by, right? So maybe I want to go from 1 to 1,000, but in jumps of 100. Okay, now it kind of gives me a little bit, smaller of output here, right? And what I can kind of see is that marginal effect, as I have higher population amounts, it must be that the effect that that's having on the number of cases, not only is it increasing, but it's doing so at an increasing rate. That marginal effect is actually getting larger and larger as the population of the city grew. Right? This is why, like New York City, saw crazy increases, right, in the number of COVID cases when there's more people in kind of the same area as opposed to like rural communities, right? The marginal effect of having another 10 people in my county, right, when I only have 1,000 people, having that same 10 people, even though when I'm in a city of like millions, it might not seem like that matters, but you could go into like, I don't know if there's a course here at the undergraduate level, but like network theory, those same 10 people, how many people are they going to be interacting with in a county of 2,000? Not a lot. But what about how many people are they interacting with day to day in a county of 5 million? A lot more. So it caused the spread of COVID to increase at an increasing rate. Mm-hmm. And we can get all that from data, right? We don't have to just use our intuition. We can see that's actually what happened. This was actual COVID data, right? So that margins command can be kind of nice. We can kind of create, these pretty quickly. Now, another way of doing this, even if I want all 1,000, if I put this quietly command here, it'll kind of calculate these all kind of behind the scenes, and it doesn't give me kind of all of that output. Now, we don't have a real use for this yet. This is where I would not expect you to do the next thing. But maybe I say, okay, I want to know those marginal effects, but I don't want you to show me all of this, right? So when I run that quietly command, it doesn't give me all the output. In fact, you can quietly run regressions, right? So maybe if I want to know these margins, what I could do is quietly run this regression, run the margins command. It no longer shows me the actual regression output. It only gives me the marginal effect output. Now, why would you want to do this? I don't know. Maybe you don't actually, maybe you just want to create like a nice marginal effects plot and you don't actually want to see the regression output. Now, that doesn't really matter. Like, well, it doesn't take up that much space. Why would I care? Well, let's say I have like 100 different control variables. Now my regression output's going to be crazy long. Maybe I just don't want to see it, right? But I'm just kind of more giving you some like practical, like people do sometimes use these quietly commands if they don't want to see the actual output on their screen. Right? So why I might do that with this margins command is because I don't want to see all of this. But there's an additional command, which is once I have these margins, I can plot them so that it gives me a nice visual. So some of what I was showing you in the slides, it came from Stata. What Stata will do is create or calculate that marginal effect at every single population value and then plot it on a graph for you. This makes it nice and easier, more digestible to show a general kind of population. You're trying to present your regression results to people. It might make it easier instead of telling, giving this table of marginal effects, show them that as population was going up, the marginal impact it had on the number of COVID cases was also increasing. So maybe if I'm like the government, I'm really trying to stress, if you're the governor of one of the, not governor, if you're the mayor of one of these really large cities, you really need to focus on the spread of COVID. I can show you the marginal effect is increasing at an increasing rate for cities of larger populations. So this margins plot command, it takes all those 1,000 values. I can run the quietly command so it doesn't show them all to me. But then as soon as it's done running that, we're waiting, it gives me this kind of nice visual where it shows me that, yes, population is going up. What was happening to that marginal effect or the predicted change in the number of COVID cases? It was going up, right? Even more. So we can kind of get these nice marginal effects. There's some like fancy stuff you can do where you can change the X and Y axis titles. We won't really go into that. That's more of like a presentation thing. Here, we're just focusing on getting the results. Okay. Now I wouldn't kind of expect you to create these graphs and then the actual kind of upcoming problem set, which I might post this week, but I know that we're still introducing this idea of nonlinear. We're going to be building on a lot this week and once we get back. So you might want to start on it when I post it this week, but likely, you know, if you want to enjoy spring break, don't worry about it until you come back. It'll have more of that. It won't be due that week we come back. It'll be due the following week, right? But this is some of the stuff that we'll start using, kind of creating these squared terms, looking at the output, determine if the squared term has statistical significance. Does it look like it's a better model? We can run these joint hypothesis tests for having a queued model, all the things that we started talking about today. I think we will then kind of end there. I'm going to kind of revisit this idea of including squared terms at the beginning of Thursday's class. Well, then I think I have an interesting little example here, kind of related to some work I've done. And then we'll kind of pretty quickly get into these logarithmic regressions, which look a little bit different than just including squared and cubed terms. So before I let you get out of here, I've got one more question to pose to you that'll lead us to thinking about these nonlinear relationships and then thinking about kind of what we're doing next class. Also, you know, people watch this video in time, I guess I'm telling them as well. But notice, what do I have kind of sitting there ready to go for Thursday? We're kind of back to what we could have in-class quizzes in any class. Okay? Now, when I'm using these squared models, just to kind of give you an idea, and this will apply to logarithmic regressions as well, what variables can I not use a nonlinear model for that we've talked about? So what would create perfect multicollinearity? If I had what's 0 squared? What's 1 squared? So what type of variable can I not include a squared term for? Dummy variables. All right. And we'll start to kind of talk about the problems that might exist with certain variables with logarithmic regressions as well. Okay. So I will have those exams if you want them on Thursday's class, or if you want to stop by my office hours tomorrow, get them. I'll kind of be there. You should see all those changes I talked about the Canvas here. Like I said, hopefully in the next 30 to 45 minutes. I just want to kind of double check everything, make sure everything's getting uploaded correctly. Otherwise, we'll see you guys on Thursday. Huh?